Today is our first real lecture in AEC 459, which is reinforced concrete and masonry structures. Now, we teach this course to you in a lot of ways as though you were going to be licensed design professionals sometime in the future. Well, raise your hand if you intend to be a licensed design professional. Which would mean you would issue drawings, right? Just making sure no one raises their hand. I usually give them advice, which is this isn't the program to be in. So, but you are all going to experience reinforced concrete design. No matter what it is that you're looking at, even a residential foundation. Most residential foundations in Wisconsin are going to be made of one of two materials, concrete or masonry, right? And the footings, concrete. Now, do you need to use concrete for footings? What else could you use? You could use timbers, right? You use piles. You could use lots of rocks. Anything that's going to give you the ability to spread load. But none of those methods are used very frequently because concrete is so useful. One of the useful things about concrete is it comes to the site in the plastic state. It fills the surface of the soil in which it's going to be in contact as a footing. If you had a steel plate footing, you'd have to level it so that you didn't have any gaps below the footing. Concrete will level itself. So we see that quite a bit. And what else do we see in footings?
Rebar.
Reinforcing steel, right? Rebar is perfectly fine. I'll always say reinforcing steel because that's the kind of nerd that I am. But you see reinforcement. We don't know why, at the moment, as we sit here, you don't know why we put reinforcement in concrete. But I'm going to cover that portion of it today. And give us an introduction. You recall when we met last week, I said you would have an assignment, but then no assignment showed up. That's because I went back and looked through the notes and realized that I'd gone too fast, and I hadn't given you enough information to properly execute the assignment. So I had mercy on you, which you always get one piece of mercy every semester, and it's unfortunate to have used it so early. What we're going to talk about today are the materials that we're going to use. And those materials we're going to talk about are concrete and steel. Do you ever think about the room in which we have this class? How it's standing up? Why isn't the roof falling down on us? Gravity continues to pull on it. Any ideas? Good luck, right? Fingers crossed. Make sure we looked at the right chicken bones and they had a good pattern when we scattered them on the construction. What do you think keeps the roof over from falling down? It's not a trick question.
Concrete and steel.
Right, but what concrete and steel formed into what? Load bearing, right? Formed into a structure. The purpose of a structure is to move the loads that are caused due to gravity, and due to wind, and due to snow, and due to earthquakes, and all sorts of other things, and take those loads and put them into the soil in such a way that the soil won't fail. And so if we consider an apartment building, I don't know, where do you want our apartment building to be? How about Wuhan, China? Let's build a little apartment building there. And up here, we have a bat house. Because bats keep the insects away, right? I mean, what have bats ever done to any of us? So the bats go flying around. They eat stuff. They eat all kinds of crazy things. The bats are pretty safe because no one would eat a bat, right? So as the bats fly over, they come in, the sun comes up, so they land up here on the bat house. They climb inside the bat house and they stay there all day. They remember how much fun they had in their lives before the researcher brought them to Wuhan from the cave. And then I wonder why everybody keeps sneezing. But anyways, it doesn't matter. We're not talking about that. We're talking about load. So this bat here, to remember where the hammer is, this bat is being accelerated to the ground at a rate of 32.2 feet per second squared. Or you guys took physics here in metric, right? So 9.81 meters per second squared. Either way, it's being accelerated due to gravity, and there's a force that results. Newton tells us that force is equal to the mass times the acceleration. The mass of the bat multiplied by its acceleration due to gravity is now pulling on that building. That load has to go somewhere. And that load follows a path, which we refer to as the, because we're engineers, what would we call the path that the load follows? The load path, right? We're not very creative people. So what we would see is we have the load of the bat goes down this way. It pulls on this, which pulls on all of these, pushes on all of these things, which pushes on the foundation, which probably, in our case, pushes on a pile, which pushes onto the soil. And because we've accounted for the weight of the bat and the stuff and the people and the building itself, we're going to transmit all of those loads. And we can do that with all kinds of things. How many of you have taken Dean's class AEC 458, wood and steel design, right? Is anyone taking it concurrently with this one? Yeah, that's a great way to get whiplash, right, from breaking your neck. And so some of you have not looked at this, but we can use other materials. We can use wood and we can use steel alone to carry loads. You've all seen in light construction, you worked on stick framing, right, where we have individual pieces. You can have timber framing, and timbers are just bigger, larger pieces. And steel framing is we build a frame, and that's what's holding up this building. You can see there's 1, 2, 3 reinforced steel columns here. If we pop one of these up, this is how you inspect for bats in Wuhan, I understand. And so if we look up here, there's a beam up there. You have to take my word for it. There's a beam, and the beam also ties to that column, and the beam runs this way, and we have a frame, a 3D space frame that carries all of our loads. And that's wonderful, so that the building will stand up and withstand the loads. And the interesting thing is, if we were to blow out all these walls in here, which are only demising walls to keep the hallway separate from the classroom, and we were to blow out all the brick out there, take the roof off, the frame stands all by itself. The frame is the bones, it's the skeleton of the structure that carries those loads. And as designers, we look at where all of those loads are when the building is up. But as a contractor, you're going to encounter the building before it's there. And so you need to make sure that at all times that you're building it, that the structure is safe. So that's one of the reasons you take this course. Secondly is, you don't just get to build whatever you want, right? You have to build it to the plans. And in order to build it to the plans, what's the first fundamental thing you have to be able to do? You have to be able to read them. So the second thing we're going to do in this class is we're going to understand what the drawings look like for reinforced concrete structures and for masonry structures. They're quite similar. And how to read them. If you've taken Dean's class, does he go through a column schedule and a beam schedule? So we'll have the same thing. But the column schedule and beam schedule will be a little different, because if I call the steel mill up and say, hi, it's Kevin, I'm the president of Kevco Construction, what I really need is an I-beam with a flange thickness of 13/64 of an inch. Want it to be, the top flange should be 18 2.25 inches. Need the web to be 2'7", maybe 2'8", but no smaller or larger than that. Bottom flange the same size, and make the web out of, I don't know, 1/2 inch thick steel. And what else do I want? I want it to be made of a special steel recipe, and I'll mail that to you. What's the steel mill going to say? You say, look, buddy, here's the sizes we have. You pick whichever one you want. Much like Henry Ford, right? You can have any color, you can have Model T, any color you want, so long as that color is black. So the problem with steel and wood is they come in standard sizes. It's not the problem, but it is an obstacle. Concrete structures can be made to order because concrete structures are built on site using molds that we call forms. So we have a lot more flexibility. The other difference is if I call up that steel mill and say, okay, look, I got it. I want an A36 piece of steel. I figured that out. I need it 250 feet long. What's the problem there? Hopefully, as long as the steel mill is on my site, it may work. If I have to transport it on the highway system, it's not going to work. But I can cast a beam out of reinforced concrete 250 feet long. You do it in relatively short order. And so one of the advantages is I can have long continuous members. And long continuous members means I don't have any of those nasty connections, right? Where I have to go in and have a torque wrench and set the torque on the bolts all to the right number. I can have them go continuously. I don't need connections between the columns and the joints that are mechanical because I can bond them together. So there's some significant advantages. And we've been using concrete for quite some time, but reinforced concrete and steel really could become available about the same time in the latter half of the 19th century. Anybody, for a piece of trivia, know what the first person to make reinforced concrete was making? Flower pots. The flower pots would crack, so he put some steel mesh in them thinking, well, that's got to help. And it does. They also made canoes and boats before they made structures. But we've got some interesting properties of our concrete that allow us to design so that in this bat lands here, it doesn't fall down with the rest of the structure. Get turned into bat fried rice, and well, you know the rest of the story from there. So let's spend a few minutes and look at our materials. Our first material we're going to look at is concrete. I know I had at least half of you in concrete class, right? How many took concrete from Heath Wiley? Okay, so tell me something about concrete, the Heath Wiley people. Aggregates, very good. What other property do we care about? What the aggregate particle size distribution is. I'm going to steal all your jokes. That was a while ago. Cement, yeah. Oh, yeah, the ingredients, yeah. And aggregates, that works, right? It's like French bread, right? What are the ingredients to proper French bread? Yeast, water, flour, and salt. Anything else is you're tarting it up. But for concrete, we can make some things. But what property do we care about a lot?
Compressive strength.
The compressive strength. Very good. Concrete has compressive strength, right? Give me an idea, what kind of compressive strength would you usually encounter? You guys have been on construction sites. That's why I get you seniors. You've seen people order concrete. In fact, yes, sir.
4,000 psi.
4,000 pounds per square inch. When?
Are most sidewalks at?
Yep, that's right.
Concrete pad.
Sure. Yeah, 4,000, very common structural Material, the highway pavement out on I-94 that they've constructed there, specified strength is 4,000 PSI. So very common strength at 28 days, right? How about, and we use a symbol, F prime C, and that is the strength of the concrete in compression. The prime is compression. Like a lot of the types of classes that you take, and the ones you take from me for sure, we learn vocabulary. In this case, because we're going to do analysis, we also have to learn notation. So there will be, very shortly, on the Canvas site, a sheet of notation, because we're going to get about 10 terms in today. We're not going to do an awful lot. But one of those is F, is strength or stress. Prime is in compression, so a squeezing force. And C, concrete, right? So we've got our concrete. It's got some really cool properties. It has strength. How about, what other property might we care about? Those of you who have taken steel and wood, what is one of the things we need to know about the steel? Or the wood? If you stretch it, you need to know about its tensile strength. Okay, that's a good one. Now, if we're looking at steel, we don't worry, right? Tensile strength, compressive strength, it's all the same thing if you're steel. But when you concrete, you suck in tension. You are the Toronto Maple Leafs of tension. Pardon me to any Leaf fans, but I don't think there are any in the room, right? No. The Toronto Maple Leafs are my brothers and sisters, brother-in-law's favorite games, favorite team for some reason. I think it has something to do with masochism. And of course, they probably also like the Vikings because they also can't win the championship. So, hence the purple pen, right? So, 7 to 9 times the square root of the compressive strength. As a rule of thumb, concrete only has about 10% of its compressive strength in tension. That's not good. So if you get concrete of 4,000 PSI at 28 days, and if assume it's 8 times the square root of 4,000, what's that? So this is lesson number 1. You have to bring a calculator of some kind to class, because what we're always going to be doing are engineering calculations. So 8 square root of 4,000, for an example, is equal to 505.56, did you say? 96, we're going to call that 506 PSI. That's not very good, right? If we look at steel for strength, we have an F sub y, the yield strength, and for most reinforcing steel, almost all the time, we'll be talking about 60 kips per square inch as our yield strength. That's in tension. What's the yield strength in compression? Any idea? You must have looked at compression numbers. Don't use them very often in steel. Right? We typically have compression and tension in the same member, but we have compression members as columns. Do you remember what the compressive yield strength is? It's not a trick question. $60 KSI. Because the steel doesn't care. The steel's a metal. Metals deform by something called dislocation slip, which we don't need to talk about, where the atoms all move around like billiard balls. Concrete is a ceramic, very strong in compression, really shitty in tension. Steel is a metal. Metals will go either way. Tension, compression, it doesn't matter. They don't care. They're going to have the same performance. So we have an interesting difference here, right? We have strength. For our concrete, depends on the direction of the loading. For steel, it does not. How about the elastic modulus? Do you remember the modulus of elasticity? Someone give me the definition. So in the elastic range, the modulus of elasticity is the ratio between the stress and the strain. So if we have a stress and a strain, in the elastic region, the slope of this line is the modulus. And this is an interesting phenomena because in the elastic region, they're related by a constant, that the stress is equal to the modulus multiplied by the strain. We can talk about them interchangeably because they're the same thing. I can stress a structure or I can strain it. If I strain it, I induce a stress. If I stress it, I induce a strain. But it's kind of hard to tell the difference, right? Because I'm going to do the same thing. If I pull on it, I'll stretch it, and that'll require a force. If I pull on it with a force, it'll stretch it a certain amount. The elastic modulus, Young's modulus, is fairly old, in the 1760s, I think, if I remember correctly, looking at the properties of wires and various other things. And so the elastic modulus is important because it tells us how much things are going to deform. So let's take a look. For concrete, like everything else in concrete, it's related to the compressive strength. It's equal to 57,000 times the square root of the compressive strength. So if this is now 4,000 psi, F prime C is equal to 4,000 psi, and this is in psi as well. What's 57,000 times the square root of 4,000? Yep, very good. 3.65 times 10 to the 6 psi, or 3.65 times 10 to the 3 KSI. Does everybody know what a kip is?
Oh, it's actually 3.60, sorry, 605.
Okay. Does everybody know what a kip is? A kip's 1,000 pounds, right? It's that beautiful marriage between metric and the U.S. common system. Kilo is 1,000 pounds. So when we talk about loads, we'll talk about them in kips, because it prevents you from having to write a whole bunch of zeros everywhere. When we talk about compressive strength, we said 4,000 psi. It's also 4 ksi. And you need to watch the units, because it's very easy to fall into that trap and be off by 3 orders of magnitude, because you had something in kips and something in pounds. Similarly, some dimensions, the span of a beam in feet, some dimensions, the width of the beam in inches. So you need to make sure there's a conversion in there. So I'm going to convert you all to the metric system, because you don't need to worry about these conversions in the metric system. But then you don't get to say kips per square inch. You have to say megapascals. Kips per square inch sounds way scarier. How about steel? Right. Steel has an elastic modulus for our purpose of 29,000 kips per square inch. Not 3,600 like concrete. So the modulus of elasticity is much larger, an order of magnitude larger for steel than for concrete. And that will make a difference as we're going along. If you're ever in a position where you have to hire a structural engineer, we always ask a question. And that question when we're hiring someone is, what's the difference between strength and stiffness? Does anybody know the difference between strength and stiffness?
How much compression it has?
So strength is strength, right? How strong it is. How about stiffness?
Whether it'll bend or not?
How much it's going to bend? Excellent answer. How much it's going to bend. And so I have spared no expense in developing this demonstration for you. I stole this stake from somebody. Then there's a well pump here. So well pump is fairly heavy, at least for someone who lifts up a pencil over it. This piece of wood has a defined strength, right? So if I take this pump and I put it here, is the beam strong enough? Right? How about now? Is the beam going to be strong enough? Right? Well, it certainly is. What's the difference? Right? How much it bends. So strength is an inherent property of the materials. And that's what we've been talking about thus far, right? Compressive strength, tensile strength, modulus of elasticity. Strength is the ability to resist load. And stiffness is how much deflection you're going to get. And so in our wooden beam, and those of you watching online didn't get to see that when we loaded it this way, in this direction, it bent a lot, and when we loaded it this way, in this direction, it didn't bend, hardly at all, with a big heavy load. It was actually, most of the students were gasping at how I was able to lift that massively heavy thing. They, of course, would have had to do it with only one hand, but they were amazed that I had to take me two, right? So what's the difference? The strength is a function of the material. The stiffness is a function of the material and its geometry. Because if I turn it so that it's deep relative to the load, or shallow relative to the load, so that it's deep relative to the load, or shallow relative to the load, it has a different stiffness. What do we talk about? What property of a section do we use to look at stiffness? The thickness, very good. It's related to thickness. It has a symbol capital I. Moment of inertia, right? The moment of inertia is important. The stiffness is equal to the product of the modulus multiplied by the moment of inertia. And that moment of inertia very clearly defined for different shapes. For almost everything we're going to do, we'll be looking at rectangles. And if a rectangle has a width of b and a height of h, its moment of inertia is equal to bh cubed over 12. So the modulus is the same for the piece of wood. It's probably about 2 million or thereabouts psi. But its shape tells us how much it's going to deflect. The cross-sectional area is BH, right? It doesn't matter whether B is parallel to the load or perpendicular to the load. B times H is always the cross-sectional area. But BH cubed, the depth, is much more effective than the width. And that's an important concept to come across because we are going to be using rectangles a lot. I could make you derive this as a calculus way of doing this. Everybody in favor? Right? So we're not going to do that. But we could. There's a simple definition, and this is for a circle. We also, and we'll talk about these in circular columns, we get the modulus of gyration, which is how much it's going to spin around the center. But for right now, we're going to have a geometric property, modulus elasticity, moment of inertia, and a physical property, elastic modulus, and the product of those is the stiffness, EI. So we can increase our stiffness by increasing the moment of inertia, or we can increase our stiffness by increasing the modulus of elasticity. Now, some of you are wondering, those of you who have already taken steel are wondering, look, Dean told us that steel is the greatest stuff in the world. Why do you ever use this concrete crap? Right? Because if they didn't, what would I do for a living? Right? So why do we use reinforced concrete? And in order to do that, we have to deviate away from from science, and go to engineering, whether that's contracting or design. So we're going to do a few things. Okay. Concrete, when you purchase it on a construction site, what's the unit of purchase typically? A cubic yard is 1 cubic yard, which is equal to 27 cubic feet. Right? 27 cubic feet. How much does a cubic yard of concrete cost? Retail. If I call Haas right now and say, but I need to give him 2 hours. Give me a cubic yard of concrete here. What's it going to cost me, excluding any extra charge for small load? Any idea? Going once? It's going to be about $110 a cubic yard for good, high quality, good aggregate structural concrete. And so I can break that down, right? If I know the density of the concrete, which is 150 pounds per cubic foot, which will come up again and again. So density is equal to 150 pounds per cubic foot. And so my cost per pound is equal to $110 divided by 150 pounds per cubic foot multiplied by 27 cubic feet, right? This is in pounds per cubic foot. This is cubic feet. This is going to give me a price in dollars per pound. So what's 110 divided by all of 150 times 27? Give us our price per pound. $0.02716. So 2.7 cents per pound. That's pretty cheap. Don't you think? Especially when you do this. Who has a device that can search the internet at the moment? Reinforcing steel is a commodity. Type in price of reinforcing steel per pound. It's traded on the Chicago Mercantile Exchange.
$0.75 per foot.
Per foot. I mean per pound.
Oh, yeah. 80 cents per pound. 60 to 80.
80 cents a pound versus 3 cents a pound. Steel is expensive. A cubic yard of steel, we need to get the steel density. Yep. And steel, thank you. Steel density is approximately 500 pounds per cubic foot, round numbers. And so 1 cubic yard of steel is going to cost, I've got 500 pounds per cubic foot, multiplied by 27 cubic feet per cubic yard, multiplied by $0.80 per pound. We'll just check this. Pounds come off, feet come off. This is going to give me dollars per cubic yard. What does that come to be? 500 times 27 times 0.8. $10,800 per cubic yard. 100 times the cost. 10,800 pounds. Not an inconsequential sum, right? $10,800. So why do we use reinforced concrete? Because it's cheap and it's just as effective. And I can use little pieces of steel like this to do a lot of work. Is this an overly effective piece all by itself? Right? They always tell me that, here, grab one side of that for me for a second. They always tell me that Superman can bend a steel, that's good, that's perfect. Superman can bend a steel bar in his bare hands. It really doesn't take very much to do that, right? Steel bar. A little piece of steel can bend readily. But if I encapsulated that in concrete so it couldn't bend readily, I could use just a little bit of the $10,800 per cubic yard stuff and a lot of the $100 per cubic yard stuff to build a beam. So I'm going to make these two materials do what they do best. The steel carries tension or compression. The concrete only carries compression. If I marry those two materials together and I do it in an intelligent way so that I know where the stresses in the beam are, I can use just a little bit of steel and a lot of a very cheap material and build structures that are as good as the ones that are made of all steel. And rolled steel is expensive. The other nice thing is reinforcing steel bars, and so I had you intentionally look up reinforcing steel, look up structural steel. It's not 80 cents a pound. It's a couple of dollars a pound. Because this bar here used to be, who knows? This bar is from, you tell me where the bar came from?
Turkey?
It's from Turkey. So this could have been like a tank that was in the Second World War, melted down. Who knows what kind of steel it was? It doesn't matter because the quality of the steel and what it's made of for reinforced concrete doesn't matter. So this is the cheapest kind of steel. old washing machines, old cars, any recycled steel, just melt it in this furnace, draw it out as a wire, and roll the wire, or draw it out as a rod and roll the rod. You have reinforcement that's good for concrete. You don't need to worry about how much chromium and how much molybdenum and all these other things that go into steel. And it's pretty easy to bend. Yeah, one more time if you don't mind. And it's fairly reversible, right? So next time someone says, how's school going? You say, the professor's like Superman, he can bend bars. Yeah. All right. Then when someone comes in here and makes fun of me, I have some number 5s out there. This is a number 3 bar. Take a number 5. Now you need a machine to bend it. Right? That's a number 5. I am probably not going to try. So we're going to marry these two materials together, but it strikes me, why don't we just make the beam out of concrete, right? What if we just made the beams out of concrete? I mean, it's so cheap, don't use any steel at all. What's the potential that's going to happen? We still have to check its load, right? It might fail. And how can a beam fail? What are the ways in which a beam could fail? Very simple equation to describe structural engineering. We have demand. That's how much load we need to carry. And we have capacity. This is the load, and this is the resistance. If demand is greater than capacity, what happens? It's going to fail, right? Try to put 10 pounds of shit in a 5-pound sack. The sack's got a capacity of 5, the demand is 10, it's going to fail, it's going to burst open. So our first important equation is that at all times, capacity must be greater than demand at all times and all loading conditions. Right? We could put it on t-shirts. Capacity must exceed demand at all times, or else failure occurs. That's a very good equation. I'm sure you're used to seeing this, those of you who took steel and wood. It's the same concept. Doesn't matter what the material is. How else could it fail? It can fail in strength. What's the other property we care about? Right. What does a failure in stiffness mean? Let's go back to my little my wood example. Let's suppose that down below that piece of wood that I'm loading, that beam, I have a frame, a bay window. What's going to happen when that load comes on and the bay window has to deform 1.5 inches? It's going to shatter. If we put a new one in, what's going to happen? It's still going to shatter, right? It's nothing wrong with the window. The deflection is too high. If you were to walk into a building and as you walked along it, the building kind of bounced, how would you feel? Like, get that out of here, right? Like every house in Menominee, okay. Very old wood, right? Fatigue gets into wood as well. So you could see that. Have you ever been on a bridge, stopped traffic, and felt it move? Because people don't walk on bridges. We don't make bridges as stiff as we make buildings, because we don't mind that it moves a little bit. So it can fail in stiffness. In particular, if this wall here is a demising wall, it just keeps those people in the hall from getting a free education by looking in. Only half funny. And if the beam up there deflects excessively, what's it going to do to this wall? It's going to break, right? So if you're building a demising wall, this wall probably, if they're smart, doesn't actually go all the way up to the top. There's a little bit of a gap to allow for the fact that the beam is going to deflect. But if it deflects excessively and it cracks the wall, then you have a perennial maintenance problem. So we can also fail in deflection. If our deflection is too high, then the structure will fail either because it's not safe, it doesn't feel safe to occupy, or it isn't, it's going to interfere with other things that are on the building. And one of the biggest things that you see is the exterior cladding on a building in a concrete frame is called a curtain wall, because it hangs like curtains. And if you have excessive deflection at the tip of the floors, you can start to damage those curtain walls, and water gets inside the building. That's not a good situation. So let's do a consideration of a little bit of beam theory. And this will tell us why we don't use plain concrete. There's a handout up on the Canvas site, an introduction to elementary beam theory, as a reminder for you. Those of you who are taking wood and steel right now from Dean, have you got to Euler's assumptions? Maybe you might not call them those, but for a given beam that's loaded in some way, right? I heart Wuhan. And for some way, it's loaded, right? It's got bats, it's got COVID viruses, it has masks people have discarded. There's various things on it that are causing it to load. That load causes generic loading in the beam. First thing it does is it causes shear, right? Shear is a cutting force. And we're going to assume for a moment that we're not worried about shear. It also creates a bending moment. Do you all remember what a bending moment is? Right? So bending moment is a force that causes the structure to bend. And it's a generalized state of stress. So the bending moment tells us that there are stresses in the structure, but we don't know what those stresses are. And if we have this beam simply supported so that it can move and it can rotate, then the moment at this point is equal to 0. Because that's how they are. For most of the semester, we're going to be looking at simply supported beams, because we'll look at some continuous beams, but simply supported beams are easier to understand. If I load this with a load of P in the center, then I get a moment diagram that looks like this. My maximum moment occurring at the center is PL over 4, where L is the span length. So, how many of you liked statics? It was awesome, wasn't it? And you learned about statics, and you learned the equations of statics, and then you learned about strength of materials, bending moments, and all that sort of thing. And I think, has Dean covered bending moments already? And I think he told me last night he did it this week. So if you've taken it, you've all now seen it at least twice. So I do not give you loaded beams like this and say calculate the bending moments. We're going to do it two ways. One is, and this is what we're going to do next week. One is I'll show you how to read a bending moment diagram. If you've done steel already, in fact, I take the one from the steel manual because it's really good. And then I'm going to show you wait for it, and brace yourselves, how you use calculus to calculate these. I'm never going to ask you on an exam, but I'm going to show you why you take calculus, because it does solve a lot of problems. So that's our maximum moment. And we know if we make an assumption that those surfaces that are parallel, like the top and bottom of this beam, before bending, are parallel after bending, then we can write an expression which that the stress at any point in the beam is equal to my over I, where m is the applied moment. I is our good friend, the moment of inertia. And y is the distance from the neutral axis. Neutral axis. Okay? And the neutral axis is the plane within the beam where the stresses are equal to 0. So we're going to assume, we'll do a cross section of our beam, that we have this condition. The top and the bottom of the beam. When we bend it this way, right, due to the load of our bat, we have a stress at the top. What type of stress is it at the top when it bends like that? Right, so we're bending it. What kind of stress is the top of that beam in? Is it squeezing or pulling? What's that? It's in compression, right? So the top is in compression. How about at the bottom? What's it doing at the bottom of the beam? Stretching or squeezing? Stretching, right? What do we call that force? Tension. And if we assume, which is a pretty safe assumption, that the stresses are linearly distributed in the beam, at some point, if we call the tension a positive force and compression a negative force, at some point, the stress is equal to 0, right? It has to. If you go by minus 5 from one end, plus 5 at the other, I'm going to have to pass through 0 to get there. And so we define that plane where it's 0 as our neutral axis. And we can measure a distance, the way we've sensed our forces, away from the neutral axis as y. And that's where our recipe, our equation comes from, is that the stress is equal to my over I. What assumption did we have to make? The beam isn't cracked. So, what I refer to as the extreme fiber stress, or the extreme fiber. If this was a piece of wood, in fact, it would be a fiber, and that's how old this type of analysis is. The extreme fiber stress occurs at the extremes, or at the top and the bottom of the beam. And that extreme fiber stress y is equal to h over 2, because if the tension and the compression are the same, this neutral axis in the uncracked section is in the middle of the beam. So if this is our beam and it has a depth of h, our neutral axis occurs at h over 2, so long as the beam is uncracked. So we can take a look and see what the capacity of a beam just made out of concrete is, because as soon as it cracks, it's going to fall down. Right? So let's take an imaginary beam and we're going to check see how it's done, and see what we end up with. So let's see, this is our imaginary beam. Let's make it 4 inches wide. How deep do you want the beam to be? 12 inches? Okay. Yep. Thank you. So h is equal to 12 inches. How about a span? Where do we want to span for? How far a distance should it go? 25 feet? Reasonable number? So our span is equal to 25 feet. And we're going to have that beam spanning, simply supported. Would the beam just